Today's example problems are introducing the idea of power. So with this, we're going to be solving power in two ways by looking at a feature of Dubuque, Iowa, being the Felton elevator. Felton elevator has a mass of 450 kilograms and travels a total distance of 90.2 meters. And it's going up the side of a hill, which has a total height difference of 57.4 meters. Everybody who is what's the word I'm looking for? Anti-trigonometry is celebrating today. It's being pulled by a little cable all the way up, and to get from the bottom, which we'll call 1, to the top, which we will call 2, it takes a total time, so time 1 to 2, of 2 minutes, which is going to be 120 seconds. What I want to find is the, we'll do, I'm on the board, what to find. I want to find the power that I need to be pulling up with. Some average power as it goes up the cliff. So, we have two ways to do this. We've got two power equations. So we have the first power equation, which is work divided by time, and the second power equation, which is going to be force times velocity. We will start with the work over time, because if you don't finish the video, at least you've done the one that is the larger review for what we are currently talking about in the rest of the content for class. So our first method, we are going to go ahead and we're going to look at our conservation of energy equation in order to find work, because we know we can turn work into power using our time that we have right here. So with this, what I have for my overall piece, and we'll write out the full thing, we'll say that my potential energy at 1 plus my spring potential energy at 1 plus my kinetic energy, oh, good grief, I'm off the board, I apologize. My potential energy at 1 plus spring potential energy at 1 plus kinetic energy at 1 plus my work in is equal to my potential energy at 2 plus my spring potential energy at 2 plus my kinetic energy at 2. I have given you absolutely no information about springs here, so we'll go ahead and get rid of both of those. We also don't have to worry about kinetic energy. We're going from start to stop. It starts stopped at the bottom so that people can get on it, and stopped at the top so we can ignore the kinetic energy. We're after the average amount of work. We're not worried about the fact that at certain points it's going faster versus slower. It is accelerating and decelerating. And then we have our potential energy, and almost always when we're doing these problems, one of the two potential energies should be 0, because we're always setting one line to 0. So in this case, I want this bottom piece to be 0. I'll set the 0 ground level is right here, meaning that my height for 2 is 57.4. So all I have is work is equal to my potential energy at the top of the bluff, which is going to be mass times gravity times my height at 2. Mass of my elevator is 450 kilograms gravitational constant, 9.81 meters per second squared. And I still have space for my 57.4 meters. Almost enough space. If I multiply all of those things together, the work required to pull this all the way up the cliff is 392.3 joules. And then my power is work per unit time. So I have 253,392.3 joules divided by 120 seconds. Joule per second is a watt, and I have 2,111.6 watt. I don't know why I wrote 4.6 watts. And I've solved it. Easy enough. That is using energy equation. Second way of solving this. Let's talk about my force equations. I am going to, when I'm talking about forces, draw my free body diagram. Draw it right here. I have a downward mass times gravity. I have a force pull up the hill. I have not been told of any friction. I'm ignoring friction. Friction would have been some extra work aspect there. And I have a normal force of the hill here. Okay. Sum of forces is equal to mass times acceleration. We're doing average. So if we were moving up the hill, we would accelerate at first because we start at rest, and then we'd go to an acceleration of 0, and then we'd have the we'd slow down at the very top. Technically speaking, this is offset because we've got one cart going up, the other cart going down. Makes this power a whole lot less required. But average acceleration is 0. We don't need to be accelerating. The acceleration, we start and we stop. We start and end at the same velocity, meaning our average acceleration is 0. Because if I wanted to write it out, I could say that V final is equal to V initial plus acceleration times time. And this is acceleration average because the velocities don't have to be a straight line. They could be whatever they want to be. When we're solving for them, they always have to be a straight line, but that's just because of our limits within the class. If velocity final is 0, velocity initial is 0, acceleration has got to be 0. I've made that assumption on a handful of these recent pieces, but hopefully with that you now understand and agree with me if you didn't before. So sum of forces, and I am interested in what's happening in the x. I probably should have already defined that, x and y, because when I get to my equation, I need my velocity and my force to be the same, in the same direction. So I have my forces in the x. I have a force pull in the positive direction, and in the negative direction, I've got mg, and this is going to be sine because this angle is this angle, and I don't actually have that angle yet. So this is sine theta. Although sine theta, if this is theta, sine is opposite over hypotenuse, and I don't even have to find that piece because opposite over hypotenuse is 57.4 divided by 90.2. We should probably find it so I don't throw people off. So we'll go down here, we'll say sine of theta. This is my theta. Because remember, when we're doing these free body diagrams, this theta is the same as that theta. So sine of theta is going to be opposite 57.4 divided by 90.2. And the problem here is that I don't have my calculator out. So sine inverse of 57.4 divided by 90.2, that gives me an angle of 39.52 degrees. So my force pull is going to be my mass, 450 kilograms, times gravity, 9.81 meters per second squared, times the sine of 39.52. And that whole thing comes out to a value of 2,809.23 newtons. So that's my force. Work I need force and distance. So I could now find my work and use this equation, but the whole idea behind this was to use the other equation, so I need velocity. Velocity, most basic definition, is distance over time. I mean, again, we can write x final minus is equal to x initial plus v naught t plus 1/2 at squared. We say that our acceleration is 0. Our x final minus our x initial is our change in our x. That divided by our time, which is the same as any change in time, is our velocity. We did those derivations first couple weeks of class. Distance in the x we traveled, the x is this direction, so that is 90.2 meters divided by the time it takes, 120 seconds. 90.2 divided by 120 is going to be 0.752 meters per second. That guy is solved. And with that, I can say that my power is my force times my velocity. And when I multiplied 2,809.23 newtons by 0.752 meters per second, I do get that same 2,111.6 watts. Two different ways to do the same problem. Maybe you're given information that makes it easier one way or the other. Maybe you can't use one way or the other, depending on how the problem's set up. But they both come out to the same answer. One big thing to do is make sure that this force and this velocity was this distance over the time, the force was that force. We need to make sure they're in the same direction. If they're not in the same direction, we're not calculating it correctly. So that's the example problem for the day.